All right. Hello. Welcome back to the ClusterDuck stream. I'm here today with Timo, where we'll be doing our pair programming on the CDP, our open source technology called the ClusterDuck protocol, and where we will be working on current issues within the CDP and come up with new solutions. So last week we were working on our Bloomfilter right here, where we wanted to free up more space within our packets, so therefore we can send more data at once, and that was by removing the path. Last time we got the Bloomfilter working. There are some tweaks that will need to be done, but today we're going to be focusing on backwards compatibility. We actually have another community member who actually built a custom built Bloomfilter for us, so that you don't have to use the library, which is going to be lighter weight. And they will be doing a presentation on how their Bloomfilter works, go over through the code and explaining how they wrote the code, as well as things like what are false positive chance. They already also have implemented the second Bloomfilter, so they'll be working with that with us next week, as well as also this when one is full, and it's this whole implemented part, we'll be working with them next week.
So this stream is going to be kind of a cleanup stream and working on implementing the backwards compatibility. What the Bloomfilter does, it stores if it already has seen a message flowing through the network. The other ducts actually took note of the ducts that it had already seen with the full name. So there are two different systems right now that we use. We use the Bloomfilter, which is the new one, and the old system is literally just tracking the path the data flows through, which ducts. We want to add backwards compatibility between the two because we do have a lot of networks already out in the open. A lot of community members and ourselves, we deploy to many networks already. And if we go fully to the Bloomfilter route, those won't work together. And I think from a coding perspective, if you can implement backwards compatibility, meaning your software systems will work together even if you're running a newer version, that is valuable, specifically because we have distributed networks all around, and you're not always able to update them, but you are easily able to add more ducts. So today we're going to figure out how backwards compatibility works because they're two different systems. But I think Nick is going to maybe dive in and kind of first do an example of how the old system works, so what we actually have to add to our new system, and then what the Bloomfilter does. I'm looking forward to it. If you have questions, as always, add them in the chat. It's kind of it's an organized stream, but we're definitely trying to figure out what are the exact functions we have to implement again, because last week we removed everything, the old packet formats and stuff. So there's going to be some testing. There's going to be some error handling in this stream to figure out how we can make sure if we take a duct that's like CDP version 2 point whatever, and then potentially the future Bloomfilter versions, and merge those. So
to get started, last time we were doing a lot of work on figuring out what our new CDP packet looks like. So if we go to our CDP packet here, and here we had updated, we used to have the whole path section right here, and then also we had over here, let's see, so if I bring over here, so we can maybe look at the same time, go to GitHub, and we go to ClusterDuck protocol, and we look at what we currently have, and show these side by side. Here we go. Alright, so we can see the differences. Let's see, can we see that? Alright, maybe we can zoom in a little bit more here. And let's open up that. Okay, so we made some changes here. Yeah. Okay. So we even just commented it out. Great. So we had our path offset, right? So we had an offset that told us where the path begins. So okay, so here's the, because we removed the path offset from our header.
So what the path offset did is, this is a data packet of the CDP. If you're new, you might not even know what it means, but every packet of data that travels through our mesh network has a defined format. And because of the old implementation, the data size can be variable. If you're sending hi, that's 2 characters. If you say hi Timo, that's 6 characters. So the data, because of the data packet is variable, the path, which means where it stores the previous ducks it traveled to, has a variable length. And that's why we have a path offset that tells you, hey, starting byte number 104, start looking for the paths. But if you have more characters, it could be 120, just an example. Since we took that out, our old system doesn't have a path offset anymore. We have a lot more space inside of our data packet. But yeah, please.
Yeah. So now what we had to figure out for backwards compatibility. So this is also an exploration of backwards compatibility. So we might also just decide, hey, it doesn't make sense to make this backwards compatible, and everyone should just move on, and we should just make this a version 3, and this is the new format how we're going to do it. And so we're just going to kind of just doing this exercise to see, hey, how much work would we have to put into doing backwards compatibility. So let's see. So we have our path offset right here, which we don't have anymore. It used to be in between the topic and what was this, duck type. So we need to somehow figure out, how do we recognize if the path offset exists in the packet. The thing about duck type is that there's only I think we only specify 3 different duck types. Duck type here. If we go here and go to definition, all right. So here,
Detector.
yeah. So these are the different bytes that it can be. Unknown, Papa, Mama, duck link, and detector. Let's see, maybe there's something we can do with that, is that we can check the duck type, and if the duck type, because so the path offset will always be, let's see. So technically, if you just sent 1 character, path offset would be.
We can calculate that.
Well, path offset tells us exactly where it ends. So actually, yeah. So if we look at the path offset. So 21. So the path offset. Okay, no, that's the position where the path offset is. Path offset is. Let's see. How do we use the path offset? Because if we look at this, when we are looking for it, so if we go back to the code, view code, and then we go here where all the source files are. So if we want to look in duck I think it's duck packet. So if we do Control F, data buffer. Okay, so when we look for where the path starts, it's based off of, it gives us the exact position where it is. So what that means when we look back here, it's always going to be greater than 26, right? Because the path offset gives us exactly where the path starts. So the path will always start at, if you send one character, it's always going to start at 27. Right?
There's no path offset there. It shouldn't.
No, but I'm saying if you check, so if we check, because we're checking position, right?
Mm-hmm.
Duct tape type can only be 0 through 4.
Yes.
Right?
There are 5 values: unknown, ducklink, mama, papa.
That's 0, but 0 through 4.
Yeah, got it.
0 through 4, and so if it's greater than 4, then that means that it's using the old packet format.
Okay.
So, so that should work. All right. So then, what we need to do is when we do our prepare for relay over here. So what we'll do, let's go back to CDP packet. I don't think we can use the duct type position. For the existence of strings. So what we want to do is put this into an if statement. If path, if using path, or if using path, else we're gonna do.
So I think Nick is going very fast for me, but I think what he's going to do.
So yeah, so what we want, so what I'm doing here is that I'm putting in that if we're not using, so because we want to make the decision, right? Is it using the path, or is it using a Bloom filter? If it's following. Let's see, because so here's the problem, right? If we are using the path, so if in order for the other ducks to continue, or in order for us to relay, we need to do a CRC on the data, right? We do a check on the data to make sure that it is intact. However, if we have the CRC shifted over by 1 byte, which is what would happen if we have a path offset in there, then what we're using is then what happens is that the hop count is now at 22 because it's been shifted over by 1, and so now the hop count, we're using the hop count to figure out the CRC for this data. And because now we're using the wrong value to calculate the CRZ to check against, it's going to fail every single time. So that's why it's important for us to figure out, is the packet using the path, or is it using the new format? So if it's using the new format, we're going to be able to, it will just work exactly, say, hey, at 22, that's where the CRC is. But if there is a path offset in the header, that means now we got to look at 23 for the CRC. Does that make sense? So that's why we need to have a distinction, right, of when we are doing the CRC part. So
that makes sense. And this is something you can imagine will probably fade away over time when you're kind of like that's what we said before. Like, we are not even sure if this is the right way to do it, but because we're gonna implement the old code in here as well, right? So we say if it's using the path, use this code, else use the Bloom filter code.
Mm-hmm. let's see. So what actually we need to look at, because there was a step before, that was prepare for relay. Oh yes, so prepare for relay. That would do the check, or where do we do the check for the CRC? Okay, we do the check for here in prepare for sending. Right. Okay, so we do it in prepare for sending. So do we do anything here that needs? This just adds it to the Bloom filter. Oh, but hop count position will be different. So that's a little bit of a problem. But I think we'll first solve the CRC issue over here, which I was talking about before. Okay, so app data. Okay, so here max data length, packet length versus minus header length, which means we actually will have a different header length because of the backwards compatibility. So that's a little bit annoying.
There's going to be a lot of. We're going to basically have to build two different systems.
Wait, is this for? What is this? Wait, hold on. Byte message ID. Get random bytes. What's it doing? Wait, hold on a second. What's it doing in message ID? Is this for sending a new? Why is it creating? Why is it creating another?
Create a byte array with random alphanumeric values.
Okay. Oh, this is okay. So this is not for relaying. This is for sending. So this is if you're sending a new message. Yeah, I was like, why would we do that? So prepare for relaying. Let's see. Let's look at where we are implementing it. So here we look at the Papadoc. RX packet. Receive. Okay, here. I think it's this one. Duck radio receive data.
Receive data.
Yeah. So let's read data. So does this do the CRC here? Yes. Okay. Here we go. So this is what we want to look at.
Recap for me real quick.
Yeah. So where I was trying to find was where do we do when we're relaying a packet where do we do the CRC?
The CRC is there to check if the packet is still there, right?
Yes, yeah, and here's also like the other. I'm just thinking about it right now because I'm kind of just like going off, like kind of a little spitballing a little bit here. Even if we make this backwards compatible, that doesn't mean that the old version will be able to use this one. Because remember the header is wrong.
So the only thing we can do is we can make it compatible. We can make the new one relay old packets, but we're not able to have the old one relay new packets, which is a problem. Because then there's no way. If it's a duck link, if the old ducks are duck links, they're fine. But as soon as the old ducks become mamas, we're in trouble.
Mm-hmm.
So maybe that kind of answers our whole question if backward compatibility is even a thing.
Yeah.
Because for anyone that's joining, this is kind of our thing. Bloomfilters are a whole different way of of checking if a duck already has seen his message.
Or maybe should even back it up a further step is why the path, right? So in order to prevent it's every single time we send a message over the network, it's a broadcast type. So every device that is in range will get this message. Now, how do we prevent the message from coming back as a broadcast? It's very easy for it to come back in a circle because it's not like the messages travel in a line. It kind of, it's like a radiation pattern. It kind of just like almost like a ripple effect. So that's why, it's very it's what will happen is that the message will eventually circle back to where the message originated from. And so to prevent that, we add to the end of the message is a digital signature, so that when a duck reads a packet, it checks the path, say, hey, is my name in there? If my name is in there, have I signed that packet? Then I won't send it, because I've already sent it once before, and that prevents us from constantly sending the same message, and where you can end up where you're just sending one message the whole time, and now there's no room for anyone to be able to send any new messages, which we've done to ourselves in the past.
Yeah, so this is maybe a quick example. I'm a duck, and I'm sending a message with the name Timo. That's 4 characters. That's my message ID. I send it out in the open. Nick is another duck. He receives it. He says, I have not seen Timo before. So what I'm going to do is I'm going to add my name, Nick, 4 characters again, at the end of my message. Then the packet that's at Nick now has Timo and Nick and sends it to someone else. I can receive that packet again, and what I do is I go back into the packet. I say, hey, is my name, my signature already on here? And currently we're only able to do that 6 times. There are only 6 ducks able to add their name to the packet, which limits us from building huge networks there. Mm-hmm. The Bloomfilter, on the other hand, is a whole different system. Instead of adding something to the packet, the Bloomfilter gets a message. So I'm a duck. I have a Bloomfilter in me. I get a message from Nick. The one thing I need to do is I am going to take Nick's message, do some math to it, and out of the math comes a number. I'm going to store that number in myself, inside of the duck. So I'm going to relay the message again, and when it might come back to me again, but the only thing I need to do is take the name Nick, do the math on it, and see if I already have this number inside of me. So the difference is, instead of adding it to the packet itself, we're going to store it inside of the ducks. So the whole stream started off pretty quickly, but the goal is make these 2 systems work together. The one thing we just figured out is we are able to relay messages on the Bloomfilter ducks that are getting the old ones, saying, hey, is my name already in here? If not, I'm going to add it. We just realized that we're not able to do it the other way around. So if you are a old duck that adds just a signature in the back and you're getting a Bloomfilter message, you're not able to do anything with it. Which means that if you're doing backwards compatibility, it works one way. That's a big risk for us. We don't want someone to set up a network with 2 different kinds of ducks that don't have the compatibility.
Yeah, well, it's kind of the discussion, right? Is it a problem where, that could be valuable, right? Where if you want to put new ducks in an old network, right? Mm-hmm. You still want to be getting data from the old ducks, right? Without having to replace them. The only thing that you just won't be able to do is rely on the old ducks to send the new data.
Yeah, and I think what the problem becomes there is if your Papadoc is old, or if you're relying on your mesh to carry the data, you're not able to, because if you're
the Papadoc would have to be on the new. So that's also another question. So if we look at the Papadoc, if we just take a quick look at the Papadoc, how Papadoc sends the data over the internet, right? So if we go to Quack.json, I think, which is right here. Let's look at C. So yeah, so what we do in the Quack.json is we set the path. However, what is different is oh man, we might still be off by 1 byte, but we could make it work. Where we wouldn't have this path component because it would be part of the payload, right? So if you see, if we look back at the duck packet, not duck packet, cdp packet.h. So what would happen on the Papadoc side is that this half, which would be the path, would actually be recorded as part of the data. Does that make sense?
Yeah.
So we could make this, if as long as you would have to replace the Papadoc, but the Papadoc would be able to receive data from old ducks as well, and it would still work.
It still works. I think this could be. I wish we could do like live polls. I think it's a risk because you're relying on someone to understand that it's kind of compatible in one way, but not the other way.
Well, I think part of it just say is that hey, you'll be able to receive old messages, but old ducks will not be able to relay the new format.
Yeah.
I mean, I think that's pretty quite simply, but
it is a tough one where it's easy to almost say if you're using just use the old version of the CDP or use the new version. See, because this is the other thing. The old networks only were able to have 6 ducts in them. So meaning that if you have a network set up, you would never have to replace more than 6 ducts.
Well, but though with this is also a way how you could extend the 6 ducts component, right? Is where
they keep sending.
Because the new one will be using the new Bloomfilter way. We'll be using a Bloomfilter, and it won't be continuously adding to the path, right?
Correct, but I think if we're sending from the old one, these ducts will still implement the old way of doing it. They won't use the Bloomfilter, right?
Yeah, they won't be using the Bloomfilter. But if you imagine, if you have you have duct A is an old one,
mm-hmm.
and then duct B is a new one, and then duct C is, let's say, an old one.
Mm-hmm.
How long is your path?
It's 2 ducts.
It's 2,
yeah,
right?
It flows through 2 ducts.
Yeah. So at the end of C, so it's gone through 3 ducts. It's done 2 hops. It's gone through 3 ducts, but the path is 2.
But didn't we want to implement the old adding to the path on duct number B?
Why would we?
Because otherwise we have the because I thought
you would only do that if that's for if you need a specific data point.
Got it. Okay, so you want to work on the backwards compatibility?
I'm not sure. I was like, it would be great to have backwards compatibility, but that's kind of just where the discussion is, right? Where we have on one side we have that backwards compatibility is good. It's we support the older versions, or I mean now with especially I think we're as now that we have more room after using the Bloomfilter, our header is going to change again. And so does it even make sense to make it backwards compatible and put in that extra work? I mean, this is also the discussion for going forward, right? How do we support old versions of the CDP? So that's kind of just one thing that is you kind of have to think about, because right now this header has already changed multiple times, and this is going to be this header component is going to be the one that really dictates is it going to be backwards compatible or not. Depends on how much we add or remove from this header. And we in the future we are going to add some more to the header itself, so that's something also to keep in mind. So actually maybe in that case it doesn't make sense to add more to do backwards compatibility at this moment, because we already know that now that we've implemented the Bloomfilter, we're going to change this header again. And that's actually would even roll into one of the things that that we would want to talk about today, which is message linking would affect this header.
Yeah, so quick, maybe because Bloomfilter is kind of a big question mark, we can kind of try to explain what message linking is. We have a stream.
Yeah.
We did a stream, I think number 5, 6, or 7. I have to check real quick. It's number 3. Stream number 3. We worked on this called telemetry packet linking. I think that's what we did. So
Yeah.
Nick can give you, if you maybe want to type that out on the screen, a very simple example of what message linking is.
Mm-hmm.
Quick recap: LoRa can able to transfer up to 256 bytes over its network, which meaning you have a defined set of packets, bytes you can send over our network. But what if you want to send maybe an image that's converted to bytes and it's like 500 bytes, or you have what we called before is a telemetry linking, which means you have one packet, but you want more data from that packet later into your data management system. We need a link package, which means I'm sending hi, and that's taking up my full packet maybe, and Nick wants to send something after that, and that says hi there. Now you have to make sure that whenever you receive this data, two of these are linked together. It's kind of like splitting up packets. Imagine you're writing up a lot of data to be sent, and it's over the 180 or whatever 220 data limit we have for the packet. I think
256.
but 229 bytes. So if it's over 229 bytes, you're not able to send it into one packet. So you want to send it into two packets, and at the receiving end, you want to link those packets together. We can give a quick example of how that would look like, because you need to tell the receiving duck, like, hey, this is part A, they're still waiting for part B. And this would be very helpful for many projects. I think we had some community members trying to send images, we had some people trying to send just more than 220 bytes of data. And linking them together could really, you're able to just send more data, which is valuable to us.
Mm-hmm. Yeah, so kind of just what, if we're looking at, so let's say you want to say, like, hello world. And let's say that we are only allowed to send, what's this, like, five or six. Let's say we're able to send only 6 characters, right? So what we would do is you want to split that up into 2 messages, right? You want to have, message 1, you would have hello and then a space. Let's see, let's put these in quotes. And then you would have
message number 2, say world.
Yeah, world. Yeah, and so you split it up into 2. But now though, how do you figure out that these 2 belong together? So and also, how do you tell the duck that these 2 messages belong together, and to reconstruct it? So let's say if it's something, it's one thing if we want to send it to the cloud, right, to the DMS, we can just send it. Also to keep in mind is when you're sending stuff over the mesh network, there's lots of duplicates. So already, if we have our you'll get like 5, you'll get like hello like times 5, and this one maybe times 3, depending on the paths that it takes in the network. I mean, yes, we'll get a hello and a world, but we'll get duplicates of each. So what we need to figure out is how do we know that these are linked together, and that they should be reconstructed into a cohesive message. So part of it is that every single message has a 4-character message ID. So you have like 1, 2, 3, 4 is the message ID. And then you have our payload, hello, right? And then what we could do is send a second message with the exact same message ID, right? And then world. But that's not enough, because we could just say, if they have a duplicate, check to see if they're the same. That might maybe work on a database in the cloud, but if you want to have this, on on a peer-to-peer network, right, where if you want mama duck to mama duck, so let's say if we wanted to do something like, if you're doing chat, let's say if we have a two-way chat, I need to, we can't store so much of this stuff. We don't want to display it as hello and then world. We want to display it as hello world, right? So, one way we can do that is we can add to our header some bytes. So what we could do, for example, is we could have for most messages we'd have 0, 1. Not the order, which one comes first. That's also true. Yes, good point, Terracor. So I mean, in most cases, you'll get the hello. If you send hello first, you'll get it before world. But if you get let's say if we do something like this, so something in the database it could look like, where in the database you might get hello, and then you get world, hello, and then world, hello, right? So we got what? We got, and then we get one more hello. And now all of these have the same message ID. And now how do we figure out, well, it's supposed to be just hello world. So that's why if we add into our header, if we add something saying, okay, well, normally, we can add into our header saying, telling us how many messages are supposed to be coming in series, and then also letting us know which one is which. So if we had something where, and also we want to keep this as compressed as possible, right? So if we have, let's say we have 2 bytes. So we have, if we just make another one here. So if we had something like...
There are a couple things we want to track. How many messages are part of this one message? So if it's hello, it's 1. If it's hello world, it's 2. If it's hello world Nick, it might be 3. This can go up to a big number. So we want to know how many smaller packets are part of one big packet.
So we have number total. So if we have, that tells us how many do we expect to get, right? So we have, for in this one we expect to get 2, or 0, 2, and then for hello would then come through as 0, x, 1, all right? So and then the next message we get for a world, 0, x, 0, 2. And then once these two numbers are the same, we know, okay, well, that's the complete message. Now we need to put it together. So then we can say, okay, well, or here, if we go here, this is hello, and then this is world. It's a little bit bigger. There we go. And then also we know that, and also keeping in mind that these have the same message ID. Right. So this is kind of how I'm thinking of structuring it, because then we'll be able to tell, okay, so we expect that there's going to be 2. We needed to make enough room to store for 2 payloads, and then once we say, okay, this is the same, then we know that that's that this is, the message is complete. We don't need to wait for any more. But for most messages that are not larger, we can just do, it'll have the same format, but we'll, if we just say here and this is hi, then we just know, okay, well, that's how most messages will go over the network. But like Timo was saying before, if we have an image, and so if we turn it, so one of the ways that we send images over the network is we basically take an image and then compress it and turn it into code, and that gets pretty big. So we'll have to send maybe 20 messages. So if where it's kind of going to look something like, if we have, we like say like 20, and then like the first one would come in, and it would look something like, or whatever. And so that way, when if we wanted to reconstruct this on the fly, we would be able to do that. And also on the cloud, we will be able to very easily figure out, okay, this is the order that it's supposed to be going in, as well as also one of the things that what's really nice about doing it this way is that we can also send a request. So if we're missing packets, right? So let's say we get one, packet 1 here, and then we have 0x20, and then the next one we get is actually 03. We missed one. It's actually possible. This is something that's possible to happen, especially if the network is bigger, and it's also possible that we've actually seen this before, where you'll get right after that you'll get x02. Right.
So how would you be able to request the missing packet? Does it get stored on a device?
So
or you have to remake it in a way.
Well, so that's kind of part of one of the things that hopefully further down the line is message receipts, right? Making sure that someone got it.
Before you destroy it inside of you.
Exactly.
Yeah.
And so we've been trying to be careful about doing that, especially since we do have limited space. And then also on top of it, we have to figure out how do we do that without increasing traffic too much. So one of the ways is like, once I send a message, listen to see if I get that message back. That means I know someone got it. These are things that we want to implement in the future.
And this would mean we'll have to restructure our head because we're adding 2 new values. One of the values is what kind is it?
The total.
The total. So
that's the kind of the beauty of kind of doing it this way, is that there is a number that for the total, and then also the current. So if the total is 1, and then the current is 1, then that's a complete message. There's nothing, there's no linked message coming with this one. But if he comes back with 20 and then the current is 1, then that there's multiple messages to come.
Yeah.
And so you can, and then we can also programmatically, we can put in, do we want to put that back together, or
just keep sending it,
or keep sending
and never
it,
worry about it.
Yeah, so it's more of something if we wanted to do something. Let's say if we wanted to do something with the data, before going somewhere else. I don't know. So I think we still have to think about this idea a little bit more if this is how we want to do it. This is something I kind of just thought up, but there might be a better way of doing it with maybe we only need 1 byte in the header.
Yeah, as long as it is, if the number is greater than 1, like what's the current? That wouldn't make sense because it's always 1. Yeah. I'm not sure yet. We can definitely find a way how to do messaging, and I think the goal for message linking is we want to send more data over the network, but you also want to be careful you're not sending too much, or you're limiting some ways of doing it. So because of the Bloomfilter already freed up so much space, it makes a lot more sense to work on this right now, because we already we have more space in this in the slides and in the payload.
So actually, so here's like maybe a way. So here's like another kind of spitballing way of how do we. So what we could do, instead of having a total and a current, right? What you could do is this. You could just actually do this with one byte. So all you would just need is current. And so if we had current, and so we say hello, that's so if it's so hello would be 0x01, and that's hello. And then we could have then we could have world would be actually 0xff. So this is the last one. World. So, and then for most other messages, so if we just had hi, that would just be hi. I don't know, what do we think about that? So, for if it's just a, if it's a complete message, right, there's no linking, and it's just 0, 0, right? But if there is linking, you start with 0, 1, and you just continually going up. And you can go up to 256 or 255, and then we say the last one, end. So this is the last one.
This is the last one.
It's the last one.
Interesting, because this one, pointing towards the old ones, we're only saying, hey, is this a one message or is this a multiple message packet? That's only a one, and it's a binary. It's a 1 or a 0, right? Is it one or is it multiple? I think we can get rid of that. That's a whole byte we can save by adding it, by choosing 2 values in the other one.
So we could just say, hey, here. So we have there's nothing, and then all we need to know is when it ends, right? And so we can just use the very last number. And say, hey, well, and what essentially this does, though, it puts a cap, which anyways, also this one would also have a cap on a, you would not be able to send a message larger than 256 messages at once. Or, 256, link 256 messages into one. So, which is what?
Which is a lot. 256 times 220 bytes, is about, whatever, 4,500 bytes, which, it's a lot of...
Yeah,
it's
so,
that's almost 4 kilobytes.
So 4 kilobytes, which is,
still not a lot of data, but coming from 256 bytes in total.
Yeah, so... it's definitely large when it comes to... how much we're sending, in one packet. Not that sending such a big message is ideal in larger networks, but this also could be something if, hey, you want to send a 1 kilobyte file, right, over a line, just from one area to the other, it would be slow, but it would work.
Yeah.
So that's also something that the larger that the linking gets, the longer it's going to take to transmit, which also means that this whole message or packet or message that you're trying to send is taking up a lot of airtime, and so that's something to be careful of. So it's a lot better to compress if you can, but there are some situations where this would be valuable. So it's also kind of the same, if I just go over here and continue the example, if we do it this way. So I think I'm kind of liking how we do this here. So it's the same thing where we just take this, and then it would go 0x x02, this one, and then so I think I kind of like this one. Although the only thing we don't, but here's the issue with doing this one. It sounds really great, but how do we this is really good if it's on the cloud side, right? But Well, also there are multiple problems here. So one is we have no idea how many packets we're missing. So if it just stops at this right here, 02, we don't know that we're missing 18 packets
Other
or
ones.
whatever.
Because there's no ending. It's critical. The ending byte makes.
We don't
it
know
through.
how many packets we're supposed to go through,
And that's a risk. That's a big risk.
So, maybe this sounds like a great idea, but maybe in practice it's really not.
Is it worth sacrificing the 1 byte?
Well, I think for in the future as two-way communication becomes a bit more prevalent, yes, then having this is going to be knowing how many packets you are expecting is going to be helpful. And also at the same time, if you're trying to do it on a peer-to-peer side where you have to say, okay, well, you don't want to create like it would be great if you can just create an array saying, hey, this is how big I need to make it, and then just insert the values, and then once you get the last one, once the array is full, you just insert it. So what I'm basically saying is like, once you get, so if I create another one of these right here, and so kind of just to show what I'm talking about. So if we say, okay, the first one we get is hello, and we have hello, and then like the next one is like null, right? And then we get the next one, we get it, then it's hello, and then it's world. And so now this is full, we can just do a for loop for whatever the size of it is, and just have our string equals string plus r I, and then you end up with our full message, right? So that's like something where you would be very easily be able to do, and I think for memory wise, I think this is also the safer way to do, because we in the beginning we did do a little bit of stuff with arrays, and we ended up creating a bunch of memory leaks. So that's the only thing I'm kind of just worried about for doing this kind of stuff here, is creating an array or a hash for each message ID. So something we'll have to be careful of when we're implementing. So I think it's something that we'll just need to continue thinking about.
Yeah, I was making some notes and kind of just while we're talking, figuring out like this is definitely something we want to implement. I think it should be part of the CDP. Tarker says, can we insert like an end token? I think the problem
the problem is that if you're asking ending, so this is kind of what my end token was, right? Was the last byte that you can use. But if you wanted to put like an end here, right? It's what we found that's not really a good way of doing stuff. I mean, we've done that for the captive portal. It's not best, especially since someone can use that symbol. Or even if we did like some weird ending or something like this, not only does it make it longer where you could end up with sending a third packet, right? We would need to send this as a third packet, and you kind of don't want to do that. And then also on top of it, now you have to do extra processing on these edge devices which don't have the best processing power to look through. Okay, do we find this like sequence or specific character? So. All right, so I think that might be call it a day at this. We'll continue thinking about this. We'll be bringing this up in discussion at our town halls. We have our town halls every Monday at 2 p.m. You can check us out. Check out the link in our Slack. Do we have anywhere else for where they can join? Do we have the link on?
Yeah, all the links for Slack are on the Cluster Protocol website.
But if you don't want to join Slack, but you want to join our town hall,
can
we put that on the website?
Yeah, we're going to add it on the website right now, and we're going to add it to our GitHub as well, where you can find the Google Meet link for our town halls.
Mm-hmm.
This stream was kind of like, we're literally trying to figure out some things here. That's the whole point of this stream, is we just open up our computers. Where do we left off? Think about it, talk about it. It turns out, maybe it's not been a good idea. Mm-hmm. Well, that's how how it goes. It's an opportunity for you guys to ask questions as well and be engaged. So the town halls will be linked on our GitHub from now on, so you don't have to join Slack to kind of look for it. I think it will be a lot better. And we'll put like an agenda on the website for the clusterprotocol.org, so you can see when we live stream, when is town hall, and maybe some other information and updates. So yeah.
Also follow us on social. We got that on our Twitter
at @owl_networks, Twitter, Facebook, Instagram. There's more of an up-to-date, day-to-day engagement with like what Project Owl is doing, and if you want more updates about the Cluster Protocol, definitely check out the clusterprotocol.org. So thanks everyone. Enjoy the rest of your week, and we'll be back next week.
Definitely come by next week. We'll be having another guest from University of Columbia. And they're going to be talking about more in depth of Bloomfilters and also the work that they did, and also explaining how that's going to work, and also the math behind the figuring out the false positive probability. So definitely come by, check it out, and we'll see you next week.